So, good afternoon. So, we're here today to have a conversation with Professor Daan Frenkel. And before I get on to talking to him, let me give a brief introduction for those who are not already familiar. Professor Frenkel is at Cambridge University, where he has been for the last 10 years, 12 years, before which he spent a longish stint at EMOL, in Amsterdam after his postdoctoral research. And as we all know, Daan is well known as a very versatile and important contributor to the field of molecular simulation, and has looked at a very wide range of problems in soft matter, in studying soft matter, and has made important contributions to both methodology and what we understand today in topics such as entropy-driven ordering, how to compute free energies. Everybody uses the methods that Daan developed, and understanding the role of entropy in a variety of other self-assembly processes and phase equilibria. I could go on, but I won't. For the purposes of today's conversation, there are a couple of things that are worth mentioning that go beyond his research contributions. The first of which is Daan is also the author of the Bible in the field of molecular simulation. It's called Understanding Molecular Simulation. And I always found the title very interesting because the word understanding comes first. And that sort of, it says something that whether it was intended or not, that's always been a guiding word in everything Daan does. And so not only has he written the book, he is in a very diverse set of places and audiences. He has given lectures on these things, so he's taken very seriously the responsibility of teaching the next generation of scientists and computer simulators. And the other thing that he's very well known for, which you've sampled during his scientific talks, but he also can hold forth in very, very interesting and thought-provoking ways on essentially any topic, and will tell you things that you haven't thought about. So today the idea is to sort of not spend a lot of time on discussing science directly, but to talk to Daan about doing science, what it means to him, what it has meant to him, where does he see it going, and what role scientists have in society, and how they should see their role. And so these are broadly themes along which I've sort of organized some questions along with those that some of you had. So I would like to ask Daan questions about his view of his work and contributions, what has motivated them, what has inspired them, and more general questions about the practice of computation and scientific research. And the third theme being the future, where scientific research, computational research is headed. What are the important possibilities and opportunities? What are things to worry about? And how the younger generation of scientists should prepare themselves for all of these eventualities. And the last theme, as I said, is what are important problems facing us, humanity, where science can make a contribution, and beyond the technical side of it, how should scientists see their role in society? Okay, so Okay, so let me begin with the first theme. So Daan, I don't want to ask you about any specific areas of science where you have made contributions, but I want to start by asking what work or works have given you the most satisfaction, and what made them so satisfactory?
That's a very interesting question. First of all, thank you very much for coming. I should also warn you, and I'll probably repeat it later, that you have to be very careful about what people in a late career stage say, because it may not at all be applicable to you. So take whatever I say with a grain of salt. Now, the things that I liked best in doing science are typically the moments, and they are few and far in between, the moments where you suddenly crack a problem that until that point had defied analysis. And I mean, I had that a few times. So really I talk about things maybe every 10 years or so. It's not that you do this every day. And the first example was actually during my PhD thesis, when I was studying quantum rotation of molecules in fluids, and the existing theoretical descriptions were clearly inadequate, and nobody knew how to do it right. And more or less, yeah, I mean, by thinking about it and working it out, I could formulate how it should be done. And then actually, this is also what I was doing experiments. I measured the things, and then I did simulations that allowed me to actually test, to see what was going on in the experiments. And the one thing that actually is very, very interesting, and that's not what people usually tell when they talk about research, usually research is presented as something logical, like you go from A to B to C. I shudder to think, to tell you this, but I was in Paris in 1975 doing computer simulations, and I was computing certain quantities having to do with liquids, and actually nobody had computed them before, and I didn't quite know why I computed them. And 3 months later, I developed a theory where I needed precisely these quantities. Now, this is not the way you would think theory goes, but that's, so I don't think too much that it goes in a rational way. I had similar, so I could suddenly solve a problem I couldn't do before. There was something similar when I got interested in the study of long-time tails in hydrodynamics, where there had been very important simulations by Bernie Older and Wainwright in the late 60s and early 70s. I was looking at this problem using lattice gases, so that's a discretized hydrodynamics, and I developed a trick, although you have to be careful. Algorithms almost never are discovered by yourself. They always exist in some form, but at least for me, I discovered a trick that suddenly allowed me to do calculations about 8 to 10 orders of magnitude more accurately. And that was, again, something that made it possible to see things that I'd never seen before. And there are similar things that I had subsequently in my career, where you realize I can suddenly do something that nobody has done before. Those are the things that really I found exciting. The other thing I found exciting, maybe add something to this, is the connection between different subjects. So I was talking about this computation of long-time tails, and then I suddenly realized that the same algorithm that I used, or basically the same idea that I used to do that for hydrodynamics, I could use to compute the behavior of polymer colloid mixtures, and then actually used essentially the same method to study path integrals of fermions, ideal fermions, but all the same fermions. So in simulation, you can just hop from one subject to the other and exploit the fact that in the end, there are not that many different techniques to address problems. That's wonderful.
Okay, so you mentioned Alder and Wainwright's work. Yeah. So I think one of the questions that people might want to know about your answer to is, in your own career, what have been the important milestones that you have witnessed in molecular simulation? What are the important milestones in your own work, and the major influences on your work?
Oh. Yeah, that's a very, again, a somewhat counterintuitive answer. Maybe I should start by saying something about my high school. So many people who go on in science say, it is because of a wonderful teacher I had. I had a very nice physics teacher. He was a very nice man, but he didn't understand physics. And so I learned something incredibly important. You can learn things from books. And that was an eye-opener. And if you have a good teacher, you never realize how powerful books can be. So this was great. Later on, I met people. For instance, I met Bernie Older before I actually was a PhD student. And he gave me advice, and I completely ignored it. Because he had been looking at these long-time tails in hydrodynamics, and he said, well, I've been studying the short-time dynamics of hard sphere fluids, I've been studying the long-time dynamics, maybe it's time to look at the intermediate-time dynamics. But that is typically like throwing a few crumbs to the birds. It's like this is still left over. And there's one thing in science that is incredibly important. The boundaries of what we know are very close, but they're not in the hot fields typically. It's like low-hanging fruit you will not find in very crowded orchards. Low-hanging fruit is where people don't go. The risk is that if you go where nobody goes, it will not immediately be appreciated. So you may publish something and people say, who cares, or why would you do that? But that's where the low-hanging fruit is. So people who influenced me, apart from that, in a way my PhD supervisor did, but not in the way you would expect. He influenced me because, on the whole, he was a nice man. I think he's still alive. I haven't seen him recently, but he's a nice man. He didn't have a very deep knowledge of physics or mathematics, but he had this feeling for what might be interesting problems. Sometimes he was right, sometimes he's wrong, and he was utterly fearless. He never worried at all about trespassing into another field, and so that is something extremely useful. Another person with whom I admired a lot is when I was a postdoc. I was in UCLA, and I interacted a lot with Daan Frenkel, who is, since that was actually already almost 20 years ago, passed away. But he showed that being a scientist is only one aspect. You also had to make sure that while doing science, you remain a decent human being. And so that I thought was an incredibly important lesson.
Now, since you mentioned Daan Frenkel, I just want to point out that the last conference Daan attended was at JNC. And I had a very brief interaction with him, and something extremely charming about him was the level of excitement that he had for what he was doing, and the friendliness with which he told you things that completely went against what you had published or were thinking about. There was just sort of this amazing innocence about how he did it.
Well, but that's also because in science, disagreement is actually what drives us, and disagreement is not animosity. We discuss things, and it is like people who are boxing. Hopefully people who are boxing, I don't, as you can well imagine, but hopefully people who are boxing are still good friends. And in science, you really make progress by saying, is that really true? And then sort of that makes it fun.
Absolutely. So I want to amplify a little bit something you said about low-hanging fruit. I think, and the reason I want to do it is I think this is often a very confusing issue. When people, especially at the beginning of their careers, think about what they want to work on. They want to work on something important, and they think that what's important is what a lot of people are working on.
Yeah.
So it's not a very obvious thing to slice.
I can give you one example. So the one thing that typically you should not work on is the last line in an article in a top journal, where people say, clearly this or that has to be investigated. That's like Bernie Older's intermediate time scale. It's a few crumbs for you to pick up, and you will not have an impact. On the whole, I find that very often the first page of a textbook has more deep questions, although they're never phrased as questions. And so I did, as Srikanth mentioned, I did simulations of liquid crystals, and the reason I started doing that is because I was reading the book of Dejean, or there was at that time Dejean, later Dejean and Pro, on liquid crystals, and I thought, all these things that they say about liquid crystals, you could actually test in detail by doing simulations, and at that time, nobody had yet managed to do it. So this was a wonderful open field. And of course, I was working on hardcore models for liquid crystals, like platelets, rod, etc. And I did it, and then I enjoyed it a lot. But then my colleagues in the field of liquid crystal physics said, yeah, but that's not the way liquid crystals are. They have benzene rings, and there's a CH group here and a CN group there. And so this is a bit of a game that is irrelevant. And then what was incredibly liberating for me is that I worked for a while in Utrecht, and I was in contact with the group there, colloid science group, who actually made all these particles. And suddenly my hardcore models were much more realistic than some of the so-called realistic models that people were studying using more conventional approaches.
Okay, so let me stop asking further questions on this theme, and I'd like to invite any questions that the audience may have.
I think the rule should be that somebody should ask the second question, because nobody wants to ask the first question. So if
So I want to ask about interdisciplinarity.
Yeah.
So, students like us who come from chemistry and starts doing molecular simulation, we have to learn lots of physics as well as computer science, also to work on mathematics as well. So, how to go for it? We should start jumping to the method and start doing it, get a feel for it, then go back and work on the mathematics, or we should grasp the basics properly, then jump to the field.
That's a very good question. So first of all, it is true that science is interdisciplinary and increasingly so. And sometimes people say that therefore we should have an education where people from the beginning get physics, mathematics, chemistry all mixed together. Personally, I think that that's not particularly good, because if you do that, for instance, if you do that to do biophysics, then you get people who are not particularly good in physics and not particularly good in biology. But what you do want is that you first get a very good training in one subject, say chemistry, and then you expand and make contacts with people who contact with people in the other fields. Now, how do you do it? It is a bit of a personal thing. I know that with simulation, I knew some statistical mechanics, and then at some point I had the opportunity to write my own or to program. And the best way to do it is to learn it, is just to do it, to start, and then at some point you realize that actually you have to do something, you don't know how to do it, and then you start reading, and then you find out that when you start reading, you need to know more, but this way you expand. The other thing is that if you work, for instance, in a field where you interact with biologists, you don't become a biologist, but you have to understand what they talk about. So it is not, because that is something that sometimes happens also with people who do simulation. They hear a term from another field, and then they grab it, put it into their own field, and then never give anything back, which for a while is okay in their own field, but that is not really interdisciplinary. That is, I don't know how you call that, but that's a risk, that you just take a term from another field and use it in your own field without actually really interacting. Is that answering part of your question?
So what you were suggesting is we should first get a feel of it by jumping into the field. Then when we need that it's necessary to work out on the mathematics and more basics, then we should come back and work on it.
Yeah, I mean, yes, so it is an iterative process, but there's one thing that has changed dramatically over the past 50 years, and that is that when I started, if you want to do a simulation, you wrote your program. That was the only way to do it. Now, of course, if you want to do a simulation, in particular if it's a more complex system, you would be insane to try to rewrite a program. Like if you do protein simulations, you're not going to write your own code. If you do ab initio molecular dynamics, you're not going to write your own code. However, I think that it's incredibly important that you do understand what's in these codes, and that therefore you're able to reproduce on a small scale at least parts. And that's, and Srikanth mentioned it, that we have this book called Understanding Molecular Dynamics. That's what you have to understand. And that's possibly now even more important in the past, because in the past there was no way you could do anything without understanding what you did. Now you can do things actually without understanding, and that sometimes leads to serious problems.
Right. So I just, go ahead.
Yeah, one question based on the last point you mentioned.
Yeah.
So the question is, will we ever understand how an algorithm works without actually coding it?
I think the answer is yes, at least for some algorithms. I mean, I have read about algorithms that I've never used myself, and it may well be that there are certain subtleties about how they work that I don't understand, and I would only find out if I could code the algorithm. But the core ideas, I think I could understand by just reading about it. And so, and then you can decide after that. So there's two levels of understanding. So like the global, what's the trick, why does it work, and then actually how does it work in practice, and for the second one you probably have to go a bit deeper.
Okay, now I want to amplify this point a little bit because I think, so there is sort of the series of dichotomies that people face. One interdisciplinarity is sort of a broad question of that kind. Whether you should know everything or you should approach the questions that you're working on from a certain point of view. Theory versus computation is often a perceived dichotomy, and physics versus chemistry, or physical sciences versus biological sciences, reading versus doing. So you answered a couple of them, but do you have anything more to add to this in terms of what you would sort of recommend to these
There's of course always this thing about when people have a triangle or three circles like theory, experiment, and simulation, and I don't like that, but that is because I have my own rule for judging diagrams. So I mean, increasingly in PowerPoint presentation, people have diagrams and all these things. My rule is very simple. Look at the meaning of the diagram, and if the meaning of the diagram is invariant under permutation of the entries, it's a meaningless diagram. So that's very simple. So I never quite, because I was trained as an experimentalist, I was doing simulation, and occasionally you do theory. I never saw that distinction as particularly important. So I know the first simulations I did in Utrecht was a master's student, and the department couldn't decide whether it was theory or experiment. Simulation didn't exist as a subject. It made no difference. So I think that many of these distinctions really are unimportant. The thing that is important is indeed, like, I had a background in chemical physics, and that, I mean, I try to exploit, whereas other people say have a background in biology. That is something where you can say, no, we are different in this respect, and you can teach me something, and I can teach you something. Were there other dichotomies?
Well, okay, Himanshu has a question.
When and why did you think about writing Understanding of Molecular Simulation?
When we thought about it,
Yes.
about writing it. Okay, so this is something that happened fairly gradually, because both Berend Smit and I were teaching courses. Partly we were teaching together. We had been teaching at summer schools, and maybe this is something I should stress, that Srikanth mentioned that I was sort of doing my service to the community teaching. That's not the story. I mean, that's part of the story. Teaching is learning, and I really believe that if you teach a subject, it forces you to understand it. And so the other thing is that if you teach, you get in contact with students, and then hopefully the students will question what you say. So these are things that are absolutely essential about teaching. And so because we have both been teaching at summer schools and things like that, we had some material, and then we realized that there was a book already on molecular dynamics, a very good book by Ellen and Tildesley, but it was more a how-to book. And we thought it is very useful for people to not just know the how-to, but really in some detail how by logical steps you can understand what you're doing. So this is, and I think that because we already have material, writing the first edition maybe took 1 or 2 years, and I wouldn't say full-time writing. The second edition, which came out in 2002, took less because it was just adding a few things. The third edition, which is now already 18 years since the second, we are working on it, but it is much, much harder because it cannot be just an addition to what's there. And in particular, what has happened since is that there's been a total explosion in algorithms. And so and algorithms that very often are in many ways very similar. Now, we had to make a choice, and I think we have made a choice, is are we going to include them all, or are we going to insult the majority of our colleagues and just leave most of these algorithms out and just focus on what we think are the essential ideas? And we've decided we go for the second option. I'm now officially retired, so I can afford to make some enemies, and that's what we're going to do.
So I want to go back to this question of dichotomies of theory, simulation, etc. I mean, do you not agree that there are in fact different ways of thinking about a problem when you think you're doing theory versus when you're trying to do computation?
Absolutely. No, I mean, the thing is, I think that the interaction between theory, simulation, and experiment is very strong, and is getting stronger every day. But it's absolutely not true that, for instance, simulation is taking over on theory. For instance, when I was working in Utrecht, there was a very strong statistical mechanics group or a number of statistical mechanicians in the theory department. And the one thing that you really need in simulations, if you do something new, is something where you can check that what you do is right. What is the best thing you can compare with? Exact results. For instance, simulations of critical phenomena, the fact that Onsager had solved the two-dimensional Ising model was absolutely crucial. And so there are several examples where the existence of theoretical results is something you totally need. I had it on a very small scale myself when we were looking at the dynamics of infinitely thin hard needles. And it was an algorithm to, actually computation was messy in the sense that you had to check for all kinds of ways they could collide. And at some point I thought, but I can compute the collision frequency exactly. And I computed the collision frequency and it was 1% off. Now the thing is, there are no such things as small mistakes. Either it's right or it's wrong. And so the fact that there was a 1% discrepancy meant that there was still something wrong. And eventually I found it, and then so theory and simulation, a very strong interaction. It's different skills. Sometimes people do both, but on the whole, I would say people tend to have a stronger profile in one or the other. And the same is true for experiment. I mean, many people do experiments and then also do some simulations. And very few people sort of are equally versed in everything. Maybe nobody at all.
So you said 1% error.
Yeah.
Was too large to ignore.
No,
so how do you decide if you're doing some unspecified computer simulation? 1%,
No, I mean, okay, so
problems,
the thing is, if you compare with an exact result, any discrepancy outside the error bars means that you've done something wrong. And then you have to face it. It's not that the accuracy of every calculation has to be 1% or 5% or 0.1%. You want to ask something?
How do you choose new problems? During your different phases of life, how did you choose new problems?
The one thing I can say for sure is the way you don't do it is by sitting behind your desk and think, now I'm going to do something new and original. That is not the way it works. So almost always it was either because I was well, first I was doing my own experiments, then I was, actually even with liquid crystals, at some point I was actually doing experiments on liquid crystals. My questions that I then later addressed in simulation had nothing to do with the experiments that I did, but I got intrigued. Sometimes you work with people who do experiments and they help you formulate questions, so that's what certainly happened when I was working with the people in colloid science in Utrecht. They inspired me to do simulations. And sometimes it's just that you talk with a colleague, you go to a conference, you're chatting, and you think, oh, but I can do this. I mean, to give you one example that Srikanth will know, I went to a conference of the APS in Denver in 2007, and Andrea Liu gave a talk about jamming, using a model that is, well, allows you to get very, very clear answers. Actually, not so clear as Srikanth later showed, but and then I thought, with that model, I can compute the number of distinct packings of spheres. And so I said to Andrea, I think that we can solve this with Monte Carlo simulations, but at the moment I don't have a postdoc. She said, oh, I have a postdoc at the moment, and it probably, I said, we can do it in 2 or 3 months. But I should have remembered something, because when I was a postdoc at UCLA, my primary postdoc supervisor was somebody called John McTague, who did great experiments, mainly experiments, but was also interested in simulation. And he said, whenever people make an estimate of how long it should take, multiply by 2 and go to the next order of magnitude. So 1 day is 2 weeks, 1 week is 2 months. And indeed, when I said 3 months, it was 6 years before we started getting results. And it's very fortunate that I didn't realize that at that moment. So, but the main thing is problems, except in very special cases, there are certain people who just think of something and that allows them to formulate a new problem, but usually that's not the way it goes. Usually you're inspired by something, maybe even you're angered by something. You say, this is not the way to think about this problem. Then you have to force yourself to formulate what you mean.
Thank you.
So I think the other side of the question that comes to my mind based on what you said is when do you decide to stop? Because often people, in fact, this question came up, I believe, when you're working on a problem and it's going nowhere.
Yeah.
When do you decide to stop, I guess?
That's actually a very important question, because there are 2 ways to make a career in science, and one is that you move to a certain subject, and if you're lucky, you make an important contribution, and then you spend the rest of your career expanding that. Typically, that's the route that almost all Nobel laureates have followed. You just pick problem, and I wouldn't say hammer it to death, but more or less that's what you do. But I don't have the patience for that. So that's not the way I can work. And so typically, I would say if I work on a topic, I start work, I get very excited, I do all kind of things. There may be students or postdocs working with me on the topic, they also start working on it. And I think, fine, because everything that has been published in the open literature is not my property. That's exactly what has to go on. And then I think after, say, order 10 years, I'll do something else. And so if I look at what I did, I worked maybe, my PhD thesis, I worked on that subject for maybe 5 to 7 years. Then I worked on the, phase transitions and liquid crystals for maybe a decade, maybe a bit more. I worked on the hydrodynamic long-time tails also about a decade. And then I started getting interested in self-assembly and DNA-mediated interactions. And at the moment already it's getting much less, so it's maybe 10, 12 years. So typically I have an attention span of about a decade. And then it's not that I'm no longer interested in the subject, but I think now other people should do something, because then you get a different perspective. Because otherwise you sort of have too much of an influence on how a field develops. Right? So okay, I should say that's not the way to get the Nobel Prize, but it's a very nice way to do science, for me at least.
Well, at least one Nobel Prize said almost exactly what you said, which was Chandrasekhar. And after he got the Nobel Prize, he was asked this question about how he has handled this issue. And he said, about 10 years. He's taken up a problem, he's worked for 10 years.
But I would never compare myself with Chandrasekhar.
But 10 years seems like a good time frame also from his answer. I just wanted to say. Okay, are there more questions from?
What do you want to be remembered for?
That's a very good question. So let me first give you an example of what I don't want. So I have a colleague whom I won't name, who is in his late 70s, or maybe now beyond it. And at some point he said, and he got all prizes imaginable, maybe not the Nobel Prize, but pretty much everything else. So he was a highly respected, highly visible scientist. And at some point he said, yeah, I'm getting a bit on in years, and I really should retire, I think. But he said, but then 20 years from now, nobody will remember me. And then I thought, well, you should have thought about that before. Because if you want to be remembered, first of all, who will remember you? If you have a family, it's your children, possibly your grandchildren. So those people who have known you directly will remember you maybe for the next, I don't know, 80 years. Students will remember you much longer than your very senior colleagues who may pat you on the shoulder and then sort of disappear from this universe. So that, I mean, that is also not the way to be remembered. But in the end, I mean, 100 years from now, nobody remembers me. So I mean, so then you have to come to terms with the fact that you're not actually remembered as a person. So how can you do something that survives yourself? And I think, and I've seen that in several places, you can create where you work a certain atmosphere that outlives you. And in the sense that even when you're gone, if your successors maintain the same atmosphere, and it's really the difference between good labs and bad labs. If you have an open atmosphere where people feel free to explore new things and are collegial and sort of, well, inspired, those cultures can survive really much longer, centuries in some cases. And so I would say that possibly one of the reasons why a place like Cambridge is successful is that at least in a number of places, people have been able to maintain that atmosphere. And I would say, even though in Cambridge, in chemistry, I wouldn't really know who was the person who started, but I can feel the atmosphere. So you can create an atmosphere long after people have forgotten who you were.
Do you see any, so I have a question related to, suppose, how this science is not so popular. I mean, how can you make science popular? Means it is not so popular in India if we go universities and where we do our 12th and graduate from where. So it is not popular that what scientists are doing.
I know.
So
I mean, this is a very important question, and almost everywhere people are formulating the wrong answer, I think, because they think we have to make science fun. For instance, in high school, but not by showing people how science works, but by showing how important it is for certain applications, etc. And they try to basically convince people who were never going to study science anyway that it's fun. Whereas the fun of, if you are inclined to do science, then early on in your career, what you find out is it's easy for you. You can do it much more easily than others, and very often, at least I know this from the high schools in Europe, they try to make it a level playing field. So, I mean, if you do physics, you have to remember almost nothing because you can derive everything there and then. That's a wonderful advantage unless the courses are made such that you have to know everything by heart. And so, you must make the sciences attractive to those people who are, in principle, likely to be attracted to science. But then you also have to show that it's an exciting career. And there you have to take into account that you're competing with other fields that may seem equally exciting or maybe are equally exciting. So at the moment you see many people going, 10 years ago many people went into consultancy. Why? Because consultancy is an area where you have to do problem solving, and people with a scientific mind like problem solving. Now many people go to machine learning, and machine learning again is a field where you can explore all kinds of new things that haven't been explored. So the main thing that you can do to make science attractive is to show that people who have, first of all, to show early on that if you have these skills, you can do a lot that other people cannot do. B, that if you then continue in science, that there's all kind of really interesting things that you can do. So the worst thing you can do is to create the impression that it's just a 9-to-5 job, and that if you wait long enough, you'll be promoted from one level to the next. I mean, that is extremely dangerous science. The downside is that the career in science is extremely uncertain. So I mean, I mentioned one career advice that I ignored from Bernie Older, but there's another career advice where I was ready with my PhD, and I actually had two job offers from industries in the Netherlands. And then I went to see my external examiner, and I said, I have these two job offers, but actually I want to go postdocing in the US, which actually meant that my salary would go down because the PhD salaries in the Netherlands were very high. And he said, you must be out of your mind if you have the possibility of a permanent job in industry with God knows what salary, and you go postdocing, then that you must be insane. And I of course, completely ignored this advice. I went postdocing. But I knew I had no job security. Now, this is always a gamble, but, I mean, made life more interesting.
Sir, actually, the raising fund for science, raising the fund for science in developing countries is a big challenge.
Yeah.
So, can you advise us that how can we raise the fund for doing science? Because this is very necessary aspects for.
I think, I mean, first, this is something where I really don't know the answer. But I would think that if you can do, I mean, first of all, you have to interact with the people you want to attract. There's no, I think that direct interaction between, for instance, high school students and people who do science and like science is really important. You can't really replace that, I think, by written material or even recorded lectures. So that's one thing. The other thing is that you should show people that they can do simple things by themselves, that they can work out a problem where maybe a phenomenon they've seen every day, and help them understand that with science you can understand it quite well. For instance, I don't know, this is something you don't have so much in India, but the thing that is very interesting in Europe is that once it has snowed, it becomes very quiet. Everything is silent. And this is the silent night of the Christmas carol. Why does everything become very quiet? I mean, there is no mystery to it. The thing is that the snow is cold, and heat in the night, whatever heat is there, radiating out to the universe up there. It means that this is very cold, this is warmer, sound waves are deflected toward the soil. So sound doesn't go like that, sound goes like that. I mean, and this is something that anybody with a slight knowledge of science can understand. And so there's so many things in your everyday life that you can understand using scientific reasoning. I think that is very empowering. So if you can give those examples, people might get excited, and actually some other people will not care at all. So that's also a way of distinguishing, I think.
Once we get into PhD and research, we generally, I don't know, but we feel in India, we detach ourselves from society most of the times.
Sorry?
We detach ourselves from society.
Oh, okay.
Like no much of social interactions, and like not much of what is happening, what are the social problems we should be concerned about. And so what do you think a scientist, like a young scientist or a young student, should contribute according to you that can solve social problems?
Okay, I think that of course it is probably the most important question. But first of all, you never detach yourself from society. You are society. The question is, what could the role of scientists and young scientists be to help solve society's problem? And there's of course practical problems like climate change, etc., etc. Well, first of all, look at the role of science and science and technology during the past 2 centuries, which has completely transformed our world. I mean, it's very hard for people from the late 18th century to have, they couldn't possibly have imagined what we have now. The next century so science has been important. The next century, we basically need science to survive. The problems that are approaching us now, which is climate change, and with the climate change, I mean, sort of moving boundaries for certain diseases, pandemics due to fast air travel, we hardly have to explain that. So all these things mean that we really need antibiotic resistance. There's one thing after the other where you can say, oh, we don't stop doing science and we go back to the hunter-gatherer society, which is fine if the total world population is maybe a few 100,000 people. But with the current population, you basically have to continue doing science and doing really important science. So that's very important on an individual level. But it's something that I think is much more important even than that you can do as a scientist. And that is, scientists, surprisingly, are human. And so, because they're human, they are not saints. They may be ambitious, they may try to get better of others, they may occasionally cheat, etc. But we have something that is called the scientific method, and certainly in the sciences, it means that if you say something that is incorrect, that is testably incorrect, it will come out. And this, I mean, and this is something that I think is incredibly important, that you defend, you can say, the idea that things have to be based on evidence and have to be tested against observation. That is something that the whole of society would benefit from, and that unfortunately increasingly we see is not happening. That, I mean, the idea that evidence is in the end the alpha and omega of any kind of policy decision seems to be moving to the background. So I think that as a scientific community, we have a huge responsibility to hold people who tell nonsense to account. Say what you like, but please show me the evidence. So I think that the role of science, of the scientific method, is even more important than before. The other thing is, and that is something, science is incredibly democratic. And by this I mean that it's inclusive in the sense that it doesn't matter who you are. So if I would say, if a schoolboy from Nigeria would stand up tomorrow and say, these theories of Professor Einstein, they're all very nice, but they're wrong for the following reason, then initially people say, well, who are you to say that? But then they go check, and if it turns out that the schoolboy is right, or schoolgirl is right, then people actually are quite happy. In science, this kind of revolution we like. It's not that we want to preserve the status quo. So, and then it really doesn't matter where you come from, who you are. It's not whether you have been born into a rich family or you have people who defend you. Science is, in that sense, a great equalizer. And so I think that we have a social message in science, we have a societal message in science. And we should work on important problems.
So, I want to ask clarification with regard to the latest question. Many critics of science, in fact, accuse the scientific establishment of, in fact, not being very democratic, of engaging in a certain tyranny of the expert, and in fact not being very evidence-based when it comes to their participation in society. Right?
Okay, so I mean, there's two different things. One is the being democratic, and there people, in a sense, I think at the moment, at least some people misrepresent what it means to be democratic. I think that most people in the academic community, and hopefully also beyond, would agree that everybody should have equal chances, equal opportunities. So that is like what in the US Constitution says, we hold the following for self-evident, that all men, etc., are born equal. So you should have equal opportunities, but then you don't have equal abilities. I mean, it's like, you will not believe it, but I would not be a good basketball player. And you can see that, why that is. And so I don't object to that. I don't claim that should be the case. But when it comes to societal questions where science plays a role, there is a tendency to think that every opinion is of equal value. But that's not true. I mean, if you have a debate between somebody who's been working for decades on climate science and somebody else who says, well, I feel it's not true, or there's no, then that's treated like you should give both opinions equal time. No, you shouldn't. So if, in that sense, I'm not democratic. I think that I'm democratic when anybody can say what they want, but they have to come with the evidence. So that is one thing. And the other thing I've heard was
the question is whether, in fact, scientists behave this way.
Whether they are non-democratic. So I would say that it does happen. I mean, typically when people are in a position of power, the statement power corrupts is always a bit true, and for some people it's worse than others. I don't really see it as at the moment as a dominant effect. So sometimes people, I mean, you find that there are certain situations where a lab has been cheating, etc. And I think it usually comes out, as far as I can tell. So I mean, I know the situation quite well in Cambridge, where I was head of the department, and I think that although there were sometimes, I would say, there was friction between people, I never saw a situation where opinions were actively suppressed for power reasons. I'm sure that it happens occasionally, but I don't think that these things will survive precisely because in the science you're either right or you're wrong, and it can be demonstrated.
Yeah. No, I was trying to ask you something slightly different.
Okay, sorry.
I think that there's sort of the world of the scientist in his laboratory and among his or her peers, and the world of the scientist as an expert who advises governments and faces the public.
Yeah.
And is there something inherent in the psychology of the two or the culture of the two which is different, even though it's the same scientists who are participating in the two cases? Because, you know, if you're talking to a peer,
yeah,
it's sort of, I think psychologically and culturally very easy for us to say, yeah, you know, what I was saying is not quite right. Whereas if you're making a press statement about what the government's position is on climate change, people probably expect that you know everything and that, you know, you're not going to change your statement as you speak.
No, okay, that's again a very important point, that we know nothing. We have hypotheses. We have increased, and some of them we really believe so much that we think that they are, to all intents and purposes, that they are true, until somebody comes and shows that there's something wrong with the hypothesis. Society typically assumes that scientists will prove things. We prove nothing. We can disprove things, but we never prove anything. And so when people say, can you prove that there's global warming? Of course you can't prove that there's global warming. You can say that all the available evidence that we have is compatible with the idea that the temperature is going up. And you can even give a simple example. Why would the temperature be going up? Well, if you have a wash basin and you turn on the tap, then the water will flow in and it will flow out. And then it's like sunlight coming in, energy coming out into the universe. And then you say, and what happens now if I add a number of hairs in my wash basin, or if you add carbon dioxide to the atmosphere? And you can say, well, I don't really know. It may go up, it may go down, but we all know it will go up. And so it is at that level that we can say things to government. What we should not do is to pretend that we know things about which we know nothing. And some scientists have no hesitation doing that, just as other people who are, typically you'll find this very often among celebrities, who express opinions about everything about what they know, about which they know nothing at all. We should really make sure that when we make a statement with some degree of authority, that we can back it up.
Sir, my question is a slight digression from the ongoing science and society topic. I hope we'll come back to that. So the thing is, we have this simplistic Lennard-Jones and Coulombic interactions approach to model materials and systems, which actually captures a lot of the properties and phenomena. When we also have this all-atom chemistry specific force field approach to looking at various phenomena. And I work with force fields, and sometimes it's a little frustrating trying to refine the force field because it will give certain properties better. At these times of disappointment or frustration, can you tell us a little bit about what we can tell ourselves about the future of these two, how they're both important for the future, something that we can tell ourselves at such a time?
I will try to, but the point you raise is indeed very important. First of all, you have to distinguish between the different roles of simulation. You can use simulation to predict the properties of materials. I mean, just reproducing the properties of materials is not as such interesting because that's already known. I mean, if I predict the melting point of ice, I know the melting point of ice. But you can predict the properties of material, like people have predicted the freezing point of iron in the core of the Earth. Those are things where you need as good a force field as you can possibly get. And in developing these force fields, you need to do simulations where you can compare with experiments. So you do validation wherever possible. And indeed, then you find that the force fields are not good enough. I think, but I mean, that at least if the developments going on now persist, and it seems likely, that increasingly force fields of that level, I think they will be completely redesigned using machine learning. In the sense that you have data, large data sets, either experimental data set and sometimes simulation data set, and for instance, you have ab initio data. How do you extract information with a force field? Well, you train, say, a deep neural net or whatever your favorite method is, and you get a cheaper description of the force field. Then somebody else can come along and say, oh, I want to do it differently. And more or less, because all the data are there and hopefully accessible, it is just a matter of trying some other algorithm. And then that bit would not be as painful as you now describe. Because I agree that it is so painful that whenever I got to a point in a project where, for instance, a student said, actually, we find that this force field is not good enough. And then she said, shall I try to optimize? I said, no, your PhD is only 3.5 years. Please don't. So I think that bit of simulation integrated with machine learning is certainly going to continue. There's another kind of description of systems that is not the force field where you go from fully atomistic to possibly or even ab initio to a less detailed description. But you can also go to truly coarse-grained models. But then you have to be very careful what the coarse-grained models should reproduce. And there, you can actually decide that in some cases, rather than coming from, I say, quantum simulations to atomic simulations to coarse-grained simulations, you can say, wait a minute, we have experiments, you come in at this level. So we've done experiments on the DNA-mediated binding between colloidal particles. We never computed anything about any DNA molecule. We just said the interaction, the hybridization free energy of DNA is known extremely well from experiments. You have websites where you can type in the sequence and the pH and the temperature and the salt concentration, and it gives you the binding strength. That's what we put in our model. And then it turns out that such models are very cheap, and for the purpose of what we do, they're fine. Of course, if you then want to know what happens if you add a molecule that would intercalate with DNA, you can't do it because that's not in the model. So I think that you see those two models, two approaches continuing, I would say, not independently but parallel to each other. And then, of course, the other branch is computer experiments, where you use computers to either test theories, which is very important, so that you have a theory which is approximate, you see, does it work? And the other thing is that sometimes computer experiments show phenomena where the theory is not yet there, and like the long time tails are a good example. There's then also the freezing of hard sphere fluids was a good example, where at that stage there was not a theory, and later the theories were developed. So computer simulation experiments may provide the data that will inspire theoreticians to discover new laws of nature.
So I want to broaden this a little bit because one of the questions I had in mind to ask was, from your experience sort of talking about and teaching computer simulations, you must have encountered either presuppositions or misconceptions about what computation means, and I want to make particular reference to your article which talks about the dark side of simulations. So two questions here. One is, in addition to sort of what you just said about the different roles of computer simulations, what are other important things that you can think of in that category? And secondly, to what extent should we be talking about these things a part of the pedagogy in teaching computation, and to what extent are we doing it as a community?
Okay, so I'm not quite sure I will be able to answer everything that you touch upon, but I think that if people start doing simulations, and certainly when they start doing simulations using existing packages, there's one mistake that you can make, and that is that you believe everything that you get out of the simulation. It is not that the simulations that you carry out are necessarily incorrect, but they may have been too short, or your analysis may have been incorrect. So the simulations in that respect are very similar to experiments. You can make more or less the same mistakes that you make in experiments. And again, an experiment is never false. I mean, an experiment is, they measure what they measure, but the interpretation is where things can go wrong. And I think that that's exactly the same with simulations. And you should be always extremely critical of what you do yourself. And you should also be critical of what has been published. So I mean, people always assume that if something is written in a journal, in particular in a high impact journal, it must be true, and the answer is no. So that you should always keep in mind, and that, oh, did I, no, the microphone is still there. So I think that there, you should be aware of the fact that simulations may be wrong. Now the second question is, what can go wrong with simulations? And the answer is, many things can go wrong, and I think it is useful to learn what can go wrong, but I would say don't teach that at the same level where you introduce the techniques. So first people should know the techniques, should have a bit of a feeling how it works, and then once they have this feeling, you say, well, but watch out, because this may not work or that may work for the following reason. And I think that on the whole, these problems are not sufficiently highlighted, and that's why I wrote the paper. And I should also say that I like to write papers in the style of this particular paper, because I find that many scientific articles are very impersonal. Basically, either they use the passive tense and they say it will be shown that, and if people admit it, they say we show that. But if you write your own opinion, then you can say I think that. And then people may disagree, but at least they know more or less that if they disagree, then the buck stops here. It's me who says it, and then not somebody else. So I'm not hiding behind anybody else. That's a matter of taste.
Okay.
I have another question. This is a rather personal one. I shifted my field from doing experiments to doing molecular simulations now. So, so there is, like all of us, there is a time frame in which we have to finish our PhDs, and for me, it's a little shorter than what other people have. So, I have learned a lot of stuff in molecular simulations now, and I can produce some interesting results, but the thing is, I also know that when I'm doing a certain analysis, I don't understand all aspects of it. And the moment I finish the analysis and I get something through, then my advice is to save time and go to the next thing. However, I still feel a little hollow about the things I do not understand. And there are several things like that. In your opinion, what advice would you give to me so that I can actually fill up the hollow parts?
I mean, that is always true. And actually, let me give an extreme example where I use something in simulation and I have no idea how it works. Computer graphics. How do they make these pictures? Let alone movies. I know that some people have written these programs. I'm sure that if I would spend enough time, I could make a not particularly good movie myself. But I just assume that they do it right. And there's actually quite a few things that, I mean, if you do a certain mathematical analysis, like you have to diagonalize a matrix or God knows what, then there are program packages, LinPack, etc. You may use. When I did my PhD, actually, we did spectroscopy with a Fourier spectrometer. I read a bit about the fast Fourier transform, but I can't say I was an expert on the fast Fourier transform. But at some point you think, okay, maybe at some point I want to know more. For the time being, this is enough. Sometimes there are things where you feel you really have to understand it. So I think that you must decide whether for the story that you tell others, it is essential that you understand better what you've done there. And that is your call. I mean, I cannot tell which ones those are.
Yes, sir.
So I want to end on a topic on the theme of things we don't completely understand, which you've spent a lot of time thinking about, entropy.
Well, first of all, I should say one thing, and that is that that not understanding thing is a positive thing. There's a book that was written by a professor of neurobiology at Columbia University, and it's called Ignorance. And basically, he wrote this book because he said, the way you teach science, you always teach it as a natural progression, because first we do this and then we do that, as if science can be derived step by step. But then he said, and then I go to the lab and it's completely differently. You just sort of wander around in the dark, and at some point you say you stumble onto something. And so, and he said the essential thing is to figure out where you're lacking understanding. And so ignorance in that sense is a very important thing. Now, the thing about entropy is indeed, entropy is one of those quantities that have attracted popular attention because people have I would say, a popular image of what it is, that entropy is a measure for disorder. That is very often true, but it's also equally often not true. And so I think it is really interesting in those situations to first get it clear for yourself what you mean by entropy, what properties you think entropy has, and then check, I mean, under what conditions you should use the word entropy, and under what conditions you should use something else, like information, and where maybe both concepts apply. But I mean, the problem is really that some words go from the scientific community into the popular community, and in doing so, they change their meaning. Like relativity, people say, well, everything is relative, isn't it? I mean, or people, I mean, everybody talks about like some kind of project being a black hole. Well, I mean, so there are certain things where we have to realize that words mean different things to different people. I mean, actually, there's one example that I know from my first trip to India when I was when was it? It was just after I did my, when I was changing jobs, so it was in the early 80s. And I was in the south of India, and I walked in Rameswaram or something like that. And there was a small building, and on the building, it said a huge sign says Institute for Vector Research. And I thought, what? An applied mathematics institute in Rameswaram. And then, of course, I realized that this was the vectors for malaria. So even within, so if you go from the biomedical field to the physical sciences, you use words differently. And as long as you understand that, it's not a problem. But you have to understand that people will interpret things differently.
So, yeah. I had one more question about this. I wanted to allude to, refer to the fact that this has been a recurring or probably a constant theme in the research that you have done, starting from entropy-driven ordering in systems that are not interacting otherwise, other than hardcore repulsions, to your latest work. So, I mean, for you, has this sort of meant exploring different aspects of this idea, or I mean, do you think over time the community, not just you, but the community has in fact explored new dimensions of the notion of entropy? Does it continue to change in your mind?
I think that certainly it's true that the perception of entropy and whether you can apply a concept that initially was introduced in thermodynamics, where the statement heat doesn't flow spontaneously from cold to hot, was translated into the statement that in a closed system the entropy never spontaneously decreases. Their entropy was introduced as something where you could measure the change, but you didn't know what it was. And then later people gave a statistical mechanical picture to tell us what entropy was. And I think that there you see more and more developments. Then people started applying entropy-like concepts to systems that you don't describe by normal sort of Boltzmann-style statistical mechanics. So it has expanded a lot. But I mean, for me personally, I've been interested in many aspects of where entropy impacts on science and society. I mean, actually, I should come back to this thing about climate change and the whole problem of an energy crisis. My PhD supervisor said there is no energy crisis. There's an entropy crisis because energy is conserved after all. So there's, and this is absolutely true. But I mean, the thing is that I think that the concept of entropy, certainly if you connect it with the fact that heat flowing from hot to cold is essentially a statement that systems go from a less probable state to a more probable state, has many different applications, and many of them basically haven't been formulated yet correctly or haven't been explored. So I think that there's a lot of work to be done there.
Still mysterious.
Still mysterious.
All right. So on that note, let's thank Daan for making this time to
Thank you.
talk to us. And, thank you all for coming.